Hello, my dear students, and welcome back. I know exams are coming, and this chapter, Gravitation, can feel a little heavy, right? But don't you worry one bit. We're going to make this super simple for you. Chalo, let's begin.
So let's kick things off with something we all love watching, cricket. Imagine Virat Kohli hits a massive six. That ball soars high up in the sky. But then what happens? It always comes back down to the ground. Why is that? It's not some kind of magic. It's all because of this incredible force we're going to master today.
All right, here is our game plan. Our mission for today. We'll look at Kepler's laws, then Newton's big one. We'll get into all the details about G, talk about how to escape Earth, and finally, check out how satellites just hang out up there. By the end of this, I promise, you'll be a champion of gravitation. Ready?
Okay, first things first. Let's talk about the rules of the road for the planets. Way before Newton and his famous apple, there was this brilliant guy, Johannes Kepler. He basically figured out the traffic rules for our entire solar system. Now, Kepler's first law, this was a huge deal. For ages, everyone just assumed planets moved in perfect circles. I mean, it sounds nice and neat, right? But Kepler, he proved that's not true. He showed that planets actually travel in ellipses. Think of it like a slightly squashed circle. And the sun, it's not right in the middle. It's at one of the focus points, just like you see here. So simple, but it completely changed how we see the universe.
All right, now the second law is really clever. Look at the picture. You see those two shaded areas? The law says that if a planet takes the same amount of time to travel along the two paths, then the areas it sweeps out are exactly equal. So what does that really mean in simple words? It means when the planet is closer to the sun, it has to move faster. Vroom! And when it's farther away, it can take it easy and move slower. It's like the planet is in a big hurry when it swings by the sun.
And then we have Kepler's third law. This one is all about the math, but don't worry, it's beautiful. It connects how long a planet's year is, that's its time period, t, to how far it is from the sun, which we call a. The law says t squared is proportional to a cubed. And hey, you don't have to just believe me. Look at the table. Look at that last column. For Earth, Mars, Jupiter, all at totally different distances, that number is almost the same. Amazing, isn't it? A hidden rule for the whole solar system.
Okay, so Kepler told us how the planets move, but he didn't really know why. That's where our main hero, Sir Isaac Newton, comes in. This is the master key that unlocks everything. And here it is, the big one, the master formula for gravity. F equals G times m1, m2 divided by r squared. It just means that the force, F, between any two things depends on their masses, m1 and m2, and the distance between them, r. So heavier things pull harder. But, and this is important, as they get farther apart, that pull gets weak really fast. And that G in the front, that's just a special number that makes the whole formula work. It's a universal constant.
Now listen up, because this is where a lot of students get confused. Big G versus small g. Please don't mix them up. Think of it this way. Big G is a universal constant. It's the same everywhere. On Earth, on Mars, in another galaxy. It's like the price of gold. The same all over the world, right? But small g, that's the acceleration due to gravity on a specific planet. It changes. It's more like the price of land, which is different in Mumbai versus a small village.
So let's dig a little deeper into the small g. The number you always use, 9.8 meters per second squared, that's just an average value right here on the surface of the Earth. The moment you move, say you climb Mount Everest or go down into a deep mine, that value starts to change. So let's see how. And this slide, this is a classic exam concept. It's a little tricky, so pay close attention. It's obvious that if you go up, away from the Earth, gravity gets weaker, so G decreases. Makes sense. But here's the surprising part. If you go down into the Earth, G also decreases. Why would that happen? Well, think about it. When you're deep inside a mine, only the mass of the Earth below you is pulling you towards the center. The part of the Earth that's above you is actually pulling you up a little bit. So where is gravity the strongest? Right here on the surface. Okay, time to put our knowledge to the test. Here's a very typical exam question. A body weighs 250 newtons on the surface. How much would it weigh if you take it halfway down to the center of the Earth? Pause the video right now, give it a shot. I know you can do it. Okay, ready? Let's solve it together.
See? It's just 4 simple steps. Super easy. First, we remember our formula for G at a certain depth. Step 2, the question says the depth d is half the radius, so we just put d equals r by 2. Step 3, we plug that into the formula, and look what happens. The r cancels out, and we're left with g divided by 2. The new gravity is half the old gravity. And since weight is just mass times gravity, if g is half, the weight is also half. So 250 divided by 2 is 125 newtons. Easy marks, beta.
All right, we've talked a lot about gravity pulling things down, pulling them in. But what about the opposite? What about getting away from it all? How do our ISRO rockets blast off and go to the moon and Mars? It's all about energy.
I mean, think about it. You throw a ball, it comes back. You throw it harder, it goes higher, but it still comes back. Gravity always wins. But what if you could throw it really, really, really fast? So fast that it just keeps going. Is there a speed where gravity just can't pull it back? And the answer is yes, there is.
And that magic number for our planet Earth is 11.2 kilometers per second. Just think about that for a moment. Not per hour, per second. That's incredibly fast. If you can give something that much speed right at the start, it will break free from Earth's gravity forever. It'll just fly off into space. But what if you don't want to escape completely? What if you just want to circle the Earth like our moon does, or like all the satellites that give us GPS and TV? You don't want to fall back, but you don't want to fly away either. How does that perfect balance work? Let's find out. Now, this is a key idea, so listen carefully. The total energy of a satellite in orbit is always negative. See that minus sign in the formula? That's the most important part. That minus sign means the satellite is bound to the Earth. It's trapped in what we call a gravitational well. It doesn't have enough energy to get out on its own. To escape, you'd have to give it more energy, enough to make its total energy zero or positive. Okay, my dear students, we're almost there. This slide right here, this is the most important one. This is your exam cheat sheet. Go on, take a screenshot right now. Write these formulas down. These are the ones you absolutely must remember. From Kepler's laws to escape speed, this is your key to getting good marks. And just like that, we're done. That's the entire chapter, made simple. From falling apples all the way to orbiting satellites. You have all the key ideas now. Just remember to practice with these formulas, and I know you will do wonderfully. All the very best for your exams. I'll leave you with one last thing to think about. A big question. If gravity is always pulling everything in the universe together, why hasn't it all just collapsed into one single point? Think about that. I'll see you in the next one. Bye-bye.